Okay, so welcome to my YouTube channel. I am Stephen, a student at University of Zambia. Please, may you kindly subscribe to my YouTube channel. That's the only way to support my work. And also provide suggestions, which videos, which topics you'd like to see on my YouTube channel. Okay, so in this video, I'm going to solve a problem here on initial value problem. Of course, it's a first order differential equation on numerical analysis. Okay, so we are given the problem here, which is the first order differential equation, and we are asked to show that the given IVP is well posed on the given interval. So we have the interval for t. The t values range from 0 to 1, or the y values range from negative infinity to positive infinity. And we are also given the initial condition. So we are given the value of y at t is equal to 0. So this one can be noted as what? At t is equal to 0. So, okay, this is called t naught, the initial value of t. Well, the value at that point, t naught is equal to 0. The y value at that point is called y naught is equal to 1. Okay, so the input here is then the value of the initial value of t. Okay, so this is the initial value of t, while the output here is the initial value of y. Okay, so I have to show that, okay, the given IVP is well imposed on this set here. So how do we do that? So there are two methods of doing this. So the first method, if you are given the first order differential equation, okay, dy over dt, the first order differential equation, which is given as f of t comma y. Okay, so the function here, which is f of t comma y, is well imposed on a given interval if the following condition is met. Okay, so if the following condition is met, so if f of t 1 comma f of t comma y1 minus f of t comma y2, okay, the mode of this is less or equal to some constant L, and this constant is called the Lipschitz constant. Okay, mode of y1 minus y2. So then if we're able to find what this constant is, okay, Lipschitz constant, and this L can never be equal to 0. Okay, this L is a non-zero value. Then we're going to say, okay, the given differential equation is well imposed on that given range of values of y and t. Okay, so let's check the first condition here. So we're going to use this condition. We need to find the value of L. Okay, so what we're given here, f of t comma y, is simply equal to the given differential equation, which is t squared y plus 1. Okay, so we are going to substitute. So let's find f of t comma y1. So f of t comma y1 is equal to t squared comma y1 plus 1. Similarly, f of t comma y2, this is equal to t squared y2 plus 1. Okay, now let's subtract the 2 here. So f of t comma y1 minus f of t comma y2. What do you get? Okay, so we get here t squared y1 plus 1, okay, minus t squared y2 plus 1, okay. So if you subtract this, we just end up having t squared y1 minus t squared y2, okay. So we need the mode of this, right? Okay, we need the mode of this. So you notice that according to this condition, it says f of t comma y1 minus f of t comma y2 should be less or equal to that, right? Okay, so let's see. We need to have y1 minus y2 according to this condition here. We need to have y1 minus y2 in the given modulus there. So we can factor out t squared. So t squared can be factored out. Okay, y1 minus y2. Okay, now remember that according to the given values of t values range from 0 to 1. Okay, so t values range from 0 to 1. So we need to pick the maximum value of t in this interval, right? Okay, so if you say t is equal to 1, that's the maximum value of t. So we end up having 1 squared just be 1, y1 minus y2. So as we can see, the condition here is met because we're able to find the L, which is the Lipschitz constant. Okay, and our Lipschitz constant here is simply 1. So the given ODE is well posed. So it's well posed with the L equal to 1. That's the Lipschitz constant. So if you're able to find this L, which should not be equal to 0, just a number, then you'd say that, okay, the given ODE is well posed. Okay, so that's the first method. Another method you can check is actually by using the partial derivative. So the partial derivative says that if you differentiate the given function t comma y with respect to y, okay, should get less or equal to, of course, this just need the modulus of it, less or equal to the Lipschitz constant. Okay, on that interval. So our interval, remember that our interval are the values of t from a to b. Okay, so let's find the derivative of this. So given f of t comma y, our equation is equal to t squared y plus 1. So let's get the partial derivative of this respect to y. So the partial derivative of this function with respect to y, this is just equal to t squared, okay? Have t squared. Now, you notice that on that interval, the interval given is from 0 to 1. What's the maximum value of t? So the maximum value of t is equal to 1, right? So if you substitute here, we get just 1 squared just equal to 1. So you notice that this 1 here is simply equal to the Lipschitz constant as well. So in either case, you're finding the same Lipschitz constant is equal to 1. So you can conclude that, okay, the given function is well posed on that given range. Okay, so that's for the first part. And then, by the way, in this video, I only solve part A and part B. I'll make another video for part C, where you are required to use Euler's method to solve the given IVP problem. Okay, so here I'll just focus on the Runge Kutta method. And then we are given the order of that is equal to 4. So we need to explain on that as well. So let me just clear this. Okay. Okay, so the next part says use the Runge Kutta method of order 4 to solve the IVP in party A at y of 0.2. So we're trying to evaluate this at t is equal to 0.2. And we are given the subintervals equal to 5. Okay. So our function here, which is our differential equation, is f of t comma y is given, right? Is t squared y plus 1. Okay. And we're given the interval. The interval given is what? From 0 to 1. What else we're given? We are given the initial condition. Okay. Y of 0 is equal to 1. This implies that our t naught is equal to 0, or y naught is equal to 0. So is equal to 1. Okay. What else do we need to find? Okay, so the formula for Runge Kutta method is given by so you can find the y value. Y is equal to y naught plus k. Okay, this is the simplest formula. There are different notations. Are going to say this. Some use w, so wi. Okay, this I'll call this yi is equal to w naught plus k, right? Okay, so both of them mean the same, so don't get confused with the notation. Okay, so where I here, this value here I, I'll explain what talks about actually the iterations. Okay, you are doing. So I'll explain what I mean here by iterations. Is maybe the problem just requires to do iterations, so this will be y1. If it requires to do 2 iterations to be y2, y3, so on and so forth. Okay, so what is k? So we need to find what k is. Okay, so k is given by 1/6 for 4, for the order of 4, right? We're focusing on the order of 4. So the formula for k is equal to 1/6 k1 plus 2k2 plus 2k3 plus k4. Okay, now what are these k1, k2, and k3 and k4? Okay, so how do you find those? So k1 is equal to h times f at what? Evaluating this f at t naught, y naught. Okay, similarly k2 can be calculated by using this formula, h times f, evaluating this function f at t naught plus h over 2, comma, y naught plus k1 over 2. So for us to find k2, as you can see, it requires us to first find k1. Okay, so for us to find k2, it requires us first to find k1. Similarly, k3 will be equal to h, okay, h times f t naught plus h over 2, comma, y naught plus k2 over 2. Similarly, as you can see here, for us to get k3, we need k2. Finally, k4 can be calculated as h times f t naught plus h, comma, y naught plus k3. So here, as you can see, we're not dividing anything, right? So k is not divided, similarly h is not divided. So that's how we can remember k4. Similarly, k1 and k4, their inputs are not divided by 2. Okay, so now that's how we need to get all these values of k, k1, k2, k3, and k4. Okay, now what of h? Okay, someone might be asking, what is this h here? H is simply the step size. Okay, h is simply step size. So how do you calculate the step size? So if you're given the interval, you can easily get the step size. So h is just equal to the given interval, which is b minus a, divided by the number of subintervals. Okay, a number of subintervals. Remember that A is a given interval, right? Okay. A is simply a given interval. So in our case here, the interval is from 0 to 1. So it means that our A is 0, our B is equal to 1. So our H will be equal to 1 minus 0 divided by how many intervals? 5 intervals. So this gives us the value of H to be 0.2. Now, we want to evaluate this at 0.2. That's what the question is asking us to do, right? Okay, at t is equal to 0.2. So we need to find the t at 0.2. So how get that t? Okay, so t is equal to, we need to get the values of t, right? For us to move from the starting point to that value, we need to evaluate. Okay, so t is given by the t naught plus h, right? So our t naught here, we know that is 0. Our h is 0.2. So this will be our t1. So that value of t1 just be equal to 0.2. Okay, you notice that we just have to do one iteration because we just one step size leads us to that value of t we want to evaluate. Okay, so for instance, let's say we wanted to evaluate this at t is equal to 0.6. Then with that step size given 0.2, we have to do t is 0.6. We have to do 3 iterations because we have to move 3 times for us to reach 0.6. Okay, so we're going to have t1, which is just be 0.2. We have to divide by 0.2. We're going to have t2, which should be 0.4, and then the last one, t3, will be equal to 0.6. Then we'll have stopped at that point. Okay, so since we're given t is equal to 0.2 here, we just have to do one iteration because our step size is just equal to 0.2, just one step will reach at that point. Okay, so we don't need to do more than one iteration here. So that's what I mean when I said iteration. So now let's go ahead and find those values of k. Okay, that's the first thing to find. So our k1, remember that k1 is equal to h f of t naught, y naught. Okay. Okay, so what is our t naught? T naught is 0, so our h is 0.5. So f of 0, comma, y naught is 1, right? So we just have to substitute 0, 1 in our function. And remember that our function f of t, y is just given by t squared, y plus 1. Okay, so let's substitute those values there. Okay, so we substitute the values. T is equal to 0, while y is equal to 1. So we're going to have 0.5. Our function here, in place of t, putting 0, so 0 squared. In place of y, putting a 1, and then plus a 1. Okay, so this gives us the value of k1 to be 0.5. Okay, similarly, the value of k2. Okay, so the value of k2 is simply equal to h f of t naught plus h over 2, y naught plus k1 over 2. Okay, so let's evaluate this first. So h is 0.5, f of t naught is 0, plus h, which is 0.2 over 0.2, comma, y naught is 1, plus k1. K1 we found just 0.5 here. Okay, sorry, our h is actually 0.2, not 0.5. Sorry for this. Our h is simply 0.2, not 0.5. Sorry for inconveniencing. Okay, so this is 0.2. 0.2. Okay. All right. So we can simplify this is 0.2. So even this one will be 0.2. Okay, 1. Okay. So this will be 0.2 f of O. Okay, this is 0.1, comma, 1.1. So we substitute this in our function. So we're going to have 0.2 times So our t is equal to 0.1, so our 0.1 squared times our y, which is 1.1 plus 1. Okay. So what do we get there? So this is the 0.2022. Okay, so that's our K2. Similarly, you can get our K3. Our K3 is simply equal to H F of T naught plus H over 2, comma, Y naught plus K2 over 2. So if you substitute H here, which is 0.2, F of T naught is 0, H over 2, this is just 0.1, comma, Y naught is 1, K2, K2 is 0.202, and then divided by 2, and this is equal to 0.2 F of 0.1, comma 1.011. Okay, just try to check this. 1.1011. Yeah. Okay, so if you evaluate that, okay, you should be able to get if you substitute, of course, the value of t is 0.1, so 0.1 squared, okay, times 1.1011 plus 1. If you evaluate this, you get 0.2022022. Okay, so that's our K3. Finally, we get our K4. So our K4 is simply H F of T naught plus H, comma, Y naught plus K4. So our H is 0.2, F of T naught is 0, H is 0.2, so F of 0.2, comma, Y naught plus K4, right? So our Y naught is 1, our K4 is 0.22022. And this is just equal to 0.2 F of 0.2, comma, 1.202222. Okay, and if you substitute this in a function, so in place of t, you substitute the 0.2, so 0.2 squared. In place of y, which is 1.2022022 plus 1, okay? We have 1 here from our function given, right? It's plus 1 here. Okay. So this evaluates to 0.2096176 Okay. And then next is find k. Since we found k1 to k4, we can now find the k. So k is equal to 1 over 6 k1 plus 2k2 plus 2k3 plus k4. So let's substitute the values of k. So 1 over 6. Our first k1 was 0.2 plus 2. Our second k2, our second k, 0.2022 plus k3. Our k3 was 0.2 this, right? Okay, 0.2022022. Plus K4 0.2096176176. Okay, and if here to simplify that, the value of K, okay, let me just put that everything in a calculator. Let me just do this. So remember that y1, so this will be y1 because it's just done one iteration, right? Okay, so this is the y1 at t1. Okay, so our t1, remember that is that value given, which is 0.2. Okay, so this, remember, this y naught plus k. Okay, so our y naught is 1 plus our k is the whole of that function there inside. Okay, 0.2 plus 2 times 0.2022 plus 2 times 0.22022. Wait, repetition. 20 like this. Okay, 2022022, and then plus 0.2096176176. And if you punch this in your calculator, you're able to get about 1.20 1.2030703336. So you can say therefore the approximation y1, okay, y at 0.2, sorry, y at 0.2 is approximately equal to y1, and this is equal to 1.2030703336. So as I said, please don't get confused. Some use different notations for this. Some use W, some use V, whatever it is. Okay, but I'm just taking to a one. I'm into a Y here. Okay, just the same thing. So this is our solution here. That's a value of Y at t is equal to 0.2. Okay, so in the next video, I'll solve the same problem, but now at t is equal to 0.8 using a different method, which is Euler's method. Okay, so just stick around for the next video. I hope you're going to enjoy it. Thank you. Thank you so much. May God bless you all.